Okay, so we've been looking at working with these algebraic fractions. So we're going to look now at another application of these fractions, or the same form of a fraction. And we're going to talk a little bit more about the numerical side of it rather than the algebraic side. It's something called a ratio. And a ratio is nothing more than a comparison between two numbers. For example, one possible ratio is I might have students on video, right now the students on my computer screen, compared to students in the room with me. Right now I have 5 students on the video screen, and I have 4 students in the room with me. This is one way I could express that ratio, just as a fraction, 5 over 4. I could also express it as 5 to 4 like that, or just 5 to 4 like this. I prefer to do it as a fraction like this because as a fraction, there are things that I can do with it that I would do with a fraction. Now, one thing that is different that I will note that actually occurs here, I would not change that to 1 1/4. Just like with the algebraic fractions, I would never change this to a mixed number. It's a comparison between two numbers, not 3. So it has to stay as an improper fraction. But like a fraction, there are other things that I can do with it. For example, if I look at the tables in this room, and it looks like the tables in Richmond are similar, Superior's are a little different, but if I look at the folding tables in this room, let's do a width to length ratio. The width of these tables is 18 inches, and the length, 6 foot, would be 72 inches. And just like any other fraction, I can cancel out the common name of inches, and both 18 and 72 can actually be divided by 18, which gives me 1 to 4. You will notice that in both of these ratios, the 5 students to 4 students, or just 5 to 4, and the 1 to 4 width to length ratio, there are no units. The reason is because the units canceled out. Because here we compared inches to inches. Here it was students to students. And that is one of the qualifications or requirements of a ratio, is you must be comparing two things with the same name or same label. Now, like here with this 1 to 4 ratio of width to length, once we have the ratio, the units don't matter. This could be saying, 1 inch of width for every 4 inches of length, or it could be saying 1 centimeter of width for every 4 centimeters of length. The ratio will be the same. Or it could be in feet, 1 foot of width for every 4 feet of length, or 1 meter of width for every 4 meters of length. The units don't matter in a ratio because the units of the two numbers are the same. Now, we can compare things with different, we can run into something like this. Let's say we have 2 feet to 18 inches. That is not a ratio the way it's written because, the two numbers have different labels or different names. But we can change it so that the 2 feet is 24 inches to 18 inches. And now they have the same label, so the inches cancel out. And I can reduce that. 24 and 18 can both be divided by 6 to give me a 4 to 3 ratio. Can I change that to 1 1/3? Say no. Yeah. We can't change that to 1 1/3. It stays 4 over 3. 4 to 3. It's not 4/3 in this case. It is 4 to 3. Any questions? Okay, so now the question then becomes, what happens if they don't have the same label or the same name? Well, here we were able to change it. But what if we can't? Let's say that you go for a drive. You jump in your car and you drive 365 miles in 7 hours. There is no way here, yeah, just a little casual drive, right? There is no way here that we can change miles into hours or hours into miles. They are different units, period. This is not a ratio. Cannot be made into a ratio. This is what we call a rate. So that is the first big difference between a rate and a ratio. Is a ratio has to have two numbers with the same label, and a rate is two numbers with different labels. The second big difference, we were okay with leaving this ratio as a 4:3 ratio. That's fine. But with rates, we almost always convert it into what we call a unit rate. A unit rate means that the denominator is 1. 1, whatever unit we're using. There is something called unit ratios. We just don't use them very often. It's not often that we have to have 1 in our denominator. So how do we turn that into a 1? Well, our denominator is 7. We just divide by 7. Of course, 7 hours divided by 7 is 1 hour. We have 360. Notice we divide by the numerical part, not the label. 365 miles divided by 7 is 365 divided by 7 is 52.142857143 approximately miles. Now what? Well, obviously we would run around this. We wouldn't want to go to 9 decimal places. Probably, in fact, a lot of times what we do is when we write a rate, we kind of hide the appearance of a fraction. Since the denominator becomes a 1, we would hide it like this. Let's round that to 52.14. And we'd hide the fraction in the units, in the label, miles per hour. That still means 52.14 miles over 1 hour. This is the form we needed in to calculate with it. But we just write it as a shortcut like that. In fact, sometimes we even hide the fraction that's in the units. For example, what does 23 mpg stand for? Miles per gallon. This is just a short way of writing 23 miles per gallon, which of course is just a short way of writing 23 miles over 1 gallon. Whenever you see this, you need to think this, because this is the form we needed in to do calculations with it. These rates and ratios are all around us. There are tons of them out there. Let's look at some more rates first. We talked about miles per hour and miles per gallon. Those are some pretty common ones. You might have, well, something that I'm sure all of you have experienced at some point. Let's say you work, you get paid, or gross pay, of $360 for time worked of 30 hours. The unit rate here, what would I do to convert this into a unit rate? Divide by 30. Divide by the number in the denominator. 30 hours divided by 30, of course, is just 1 hour. 360 divided by 30 is $12. So it's $12 over 1 hour, or $12 per hour. That would be your unit rate. Your hourly wage is a unit rate. In the medical field, most of your dosages are rates. You might have a dosage that is listed as, I don't know where the dollar sign is there, 2 milligrams per kilogram. What that means is for every kilogram of weight, you're giving 2 milligrams of the medication. Let's say that you have a patient that weighs 40 kilograms, and the doctor's orders are to give 200 milligrams of medication. The unit rate here, you would divide by 40. That is 5 milligrams over 1 kilogram, or 5 milligrams per kilogram. Many of our rates have time in the denominator. For example, if we're sticking with medical here, you might have 4,000 milliliters over 8 hours. So again, you divide by the 8, you get 500 milliliters in 1 hour, or 500 milliliters per hour. So time is often the denominator in a rate, but not always. For ratios, we saw a couple of simple ratios. In technical fields, in mechanical, architectural, construction, there are rates everywhere. One of them might be, now here's where we're going to stretch your imagination a little bit, because I'm going to draw a picture or two. No, that is not a sun. Any guesses? Yeah, those are gears. We're going to talk about gear ratio. Gear ratio is the number of teeth in the driven gear compared to the number of teeth in the driving gear. So obviously, if you count the teeth, this one has 12 and this one has 8. But which one's driven and which one's driving? Well, we need more information. Let's see, I draw this onto the picture. Pretend that looks like a little motor attached to that gear. If that motor is running, both gears will be moving. But if I separate the gears, one will stop. Which one will stop? The 12 or the 8? You got it. The 8-tooth gear. It's not connected to the motor. It will stop. It is being driven by the other gear. It is only turning because it's meshed or synced with the other gear. The 12-tooth gear is the driving gear. It's the one that's forcing the other one to turn. It is driving the other gear. So we have an 8 to 12 ratio. Both of those can be reduced by 2 or 4, which would give us a 2 to 3 ratio. If you divide it by 2, we just divide by 2 again. There are all sorts of ratios like this in mechanics. We're not going to go over a lot of them. Even in the medical fields, there's ratios like that for concentrations. You might have 3 milligrams of a medication to 8 milligrams of water. There's a ratio, a 3 to 8 ratio. Most often it'd be milliliters to milligrams that you'd have a ratio like that. But those are concentrations are all ratios. Another ratio in life that might be important to many of you, if you ever go to get a loan, the whole credit score is not as big of a deal as it used to be. It used to be if you didn't have a good credit score, you couldn't get a loan. Well, now the credit score mostly determines what interest rate you're going to pay. The lower your credit score is, the higher interest rate you're going to pay. But you can still get a loan if everything else works out. One of the things they look at is something called a debt to income ratio. What does that mean? Well, let's look at our debt to income ratio in an example. So let's say that you are earning about $2,000 per month. That's our income. That's before taxes. That is gross. Yes, I know that's a little low, but that's fine. Let's look at our required payments. Now, debt is not utilities. It is strictly debt payments. So let's say you have a house mortgage that you are paying $500 a month on. Let's say you have a credit card that you are paying $200 a month on. Your student loan, let's put it at $100 a month. Your current, and let's say that's all your debt payments right now. Your current debt level is $800 per month. So your debt to income ratio is $800 over $2,000. Both of those can be divided by 400, which would give you a 2-to-5 ratio. Now, if you don't see that, obviously, I would divide both of those by 100 to make it 8 over 20, and then divide by 4 to make it 2 over 5. A 2-to-5 ratio. If you were trying to buy a car, and that car payment is going to be an additional $200, now you have $1,000 in debt. Well, what's 1,000 over 2,000? That's a 1-to-2 ratio, right? Typically, by the way, right now, your banks want you to stay at a 1-to-3 or below. So $1 of debt maximum for every $3 of gross income. So the rest of that would be your, what you'd pay for gas, utilities, food, stuff like that. But they've, one of the reasons for the big debt crisis in 2007, 2008, 2009, government regulations actually forced banks, when giving home mortgages, because of the Fannie Mae, Freddie Mac stuff, they forced banks to push their requirement from 1-to-3 to 2-to-5. So that's basically from a 33% to a 40% debt ratio. And that meant that those are people now that normally would be considered unable to handle that level of debt were now being given those loans. And then, believe it or not, they couldn't handle that debt, and they defaulted on the loans, and there was a mortgage crisis. Anyway, those are some ratios that might be important in your life as you go on. Any questions? These ratios are all around us, by the way. If I had to pick one topic in math that was the single most important, most powerful topic, it is ratios. And, of course, this next step is how we work with ratios, and that is proportions. About 80 to 90% of what we do in math can be turned into ratios and proportions if you know the underlying piece of it. If any of you are going into a medical field where you have to take the math for health professionals, literally 80% of that course is just dealing with ratios and proportions and working with them properly. So, what is a proportion? Well, let's say that you need to keep that 1-to-3 debt to income ratio. You're applying for a loan. Your current monthly income is $3,600 gross. By gross, I mean before they take out your taxes and stuff on your paycheck. So what that means is, if you want to figure out how much debt payments you can afford per month based on that income, use the 1-to-3 ratio. You set up a second ratio that's equal to it. What does the 1 represent here in this ratio? That represents the debt. The 3 represents your income. Whatever numbers we put on the other side here, this top number has to represent your debt as well. The bottom number must represent your income. So the 3,600, which one does that represent? Debt or income? Income. So the 3,600 has to go on bottom. That's one of the nice things about a ratio or a proportion is they're easy to set up because they have to represent the same things on each side. So now, to find this missing number, we're dealing with equivalent fractions. There are a couple of ways we can deal with this. Just like we did when we were trying to rename a fraction, we can decide, okay, what do we do with the 3? Well, we multiply by 1,200 to get 3,600, right? If you didn't see that, just 3,600 divided by, what's that? I don't know why I put divided in there. Times 1,200, there we go. If we didn't see that, you could just done 3,600 divided by 3 is 1,200. So 1 times 1,200 is 1,200. So that's saying you could afford $1,200 of debt. That process, however, is pretty tedious. If you look at what's happening there, the 3,600, you take the 3,600 divided by 3 to get the 1,200. And then you take that 1,200 and you multiply the 1 by it, right? So what we are doing is we're taking this 1 here. So taking that 1 and we are multiplying by the 3,600 divided by 1,200. Where did the 1,200 come from? 3,600 divided by 3. Because of that, there's a process. The shortcut is, they call it cross multiply and divide. So what we're doing is we're just going to multiply the 1 times 3,600 and then divide by 3, which is what we're doing here. 1 times 3,600 is 3,600 and divide by the 3. 1,200. Let me show you some examples. So let's say we need a 3-to-5 ratio. And we know that this number here is 60. To find this number down here, I would take the 2 numbers that are on a diagonal. Which 2 numbers are diagonal from each other? 5 and 60. I am going to multiply those. What is 5 times 60? 300. What number is still left? The 3. I am going to divide by the 3. That would be 100. So 3 to 5 is the same as 60 to 100. Those are equivalent ratios. Technically, what is happening here? I'm going to put X in there for the missing number. In a proportion, when we are solving for that missing number, what we are doing is not really cross-multiplying and dividing. We are actually cross-multiplying in both directions. This diagonal is 5 times 60, which is 300. This diagonal is 3 times x, which is 3x. In a proportion, those two cross products, is what they're called, must be equal. So the 300 must be equal to 3x. How do we solve that equation? Divide by the 3 to get x by itself. Very good. So divide by the 3, you get 100. So it's really the same process. You're just shortening it up by not writing out the equation. So why did I even bother showing you this if we can just cross multiply and divide right in the proportion? Well, because it's not always that simple. We're going to get to that in just a few minutes. Don't want to totally scare you away quite yet. So let's give you one like 7/3, and let's say I know that this number here is going to be 42. Find that missing number there. Why? So again, there's a couple ways we can do this. I'll do it the short way. 3 times 42, 126. Then the number that's left is the 7. We divide by 7, which will give us 18. So this is 18. How many of you came up with 18? Good. That's not so bad, is it?
Of course.
You've caught on to a pattern here.
And the day wasn't over yet. It's all about the pattern.
Oh yeah, it is. How about this one? This one we cannot just cross multiply and divide, can we? But we can do what I just showed you, just simply cross multiply. So going on this diagonal, we have 5 times 12, which is what? 60. Good. On this diagonal, we have 2 times 3x, which is 6x. The relationship between those two is that they must be equal. 6x must equal 60. So what do we have to do? We have to divide by 6. Very good. 60 divided by 6 is 10. X is 10. Now, depending on what we're asked for here, if we're asked just to find x, we're done. X is 10. If we're asked to find out what this value is, of course, this is 3 times 10, or 30. We might have something like this. Again, we can't just cross multiply and divide because this isn't just a variable by itself here. But we can do this. I have 8 times x plus 7. I'm going to have to do it that way to make it work. Okay? It's got to be put in parentheses because that x plus 7 is a single number. So what is that if I multiply it out? What's 8 times x? 8x. 8 times 7? Positive 56, so plus 56. Then going the other way, 3 times 24 is 72. So we know from this 8x plus 56 must equal 72. How do we solve that? We're going to subtract 56. Very good. 8x equals 72 minus 56 is 16. And then we divide by 8. X equals 2. So now, let you guys try. 3 over 4 equals 3 over 4 equals 15 over y minus 3. Where do we start? Is it a minute yet? Oh, I'll wait. Yes, that'd be your first step. Okay, so you do 4 times 15, which is 60. Then you do the 3 times y minus 3. So 3 times y minus 3, which is 3y minus 9. Good. Anybody want me to go back and show you how to do that? Yeah? Okay. So you got to do the 3 times y is 3y. And then 3 times negative 3 is negative 9, or minus 9. So now we know that this must equal this. So 60 equals 3y minus 9. Now we have to get the y by itself to solve it. So we have to get rid of the 3 and the 9. Which one do we get rid of first? The 9. Y was multiplied by 3, then the 9 was subtracted. So to take it apart, we reverse that. We take off the last piece first. So we add 9. So 69 equals 3y. And then divide by 3. So 23 equals y. So y is 23. Questions? Okay, so as we keep moving with this form of a number, we've looked at fractions, we've looked at renaming fractions, we've looked at greatest common factors and least common multiples, so now we are ready to jump right in and start working with fractions. So let's say I want to add 3/4 plus 1/5. When we add, what are our requirements? What's our first requirement to add? Must have the same name. And for a fraction, that is the denominator. Do these have the same denominator? No. So we're going to have to take care of that first. Once we have that same name, we add by combine the counts. And what do we do with the name? We keep the same name, right? So let's take a look here. We need the same name. For 4 and 5, what is our least? We're looking for a least common multiple, or sometimes called least common denominator. What is that going to be for 4 and 5? 20. Good. So to do this, I am going to write this vertically. We have 3/4 and 1/5. We're adding. I am going to change my denominator into 20 for both of those. Now, if we don't see that 20, there are a couple things we could do. We could make lists. We know there'd be 4, 8, 12, 16, 20, 24. If we count up by 4s, right? Adding 4 every time. 5 would be 5, 10, 15, 20. We get our first match, right? The other option is we could factor and do the factors to find the least common multiple like we were doing at the beginning of class. A third option, if you don't care if you get the least one, just as long as you get a common denominator, which actually is okay. You don't have to have the smallest common denominator. You could just multiply the two denominators, 4 times 5. In this case, that gives you the smallest one of 20. So anyway, back to this problem. We decided our common denominator was 20, so we're going to change them to 20s. So up here, what do we have to do to the 4 to turn it into a 20? We multiply by 5. That is the only thing we can do to change the name, is multiply or divide. So we multiplied by 5 to make it a 20. So what do we have to do to the top? We have to do the exact same thing. We have to multiply by 5. So 3 times 5 is 15. So down here, what did we do to the 5 to turn it into a 20? Multiply by 4. So what do we have to do to the 1? Multiply by 4, which gives us 4. Now that we have the same name, we're on to step 2. We combine the counts. What are the counts here? Yeah, the 15 and the 4 are the counts, which add up to 19. And then we keep the same name, which is the 20. So 19/20. What do you think? Better sharp stick in the eye? No?
I can live with that.
You can live with the stick?
No, with your.
Oh, with this? Oh, okay, gotcha. It doesn't get a lot worse, I swear.
Yeah.
I just had to stop for a second. There's like, maybe it does a little
Yeah,
bit.
think about that one because he knows there is.
I said a lot worse. I didn't say it didn't get worse. It doesn't get a lot worse. So let's do 3/8 plus 1/6. So I'm going to write it vertically again, because that's how I think. Common denominator. Now here's a case, if I multiplied 8 times 6, I would get 48, which is a common denominator, and it would work. But there's a smaller one, 24. Very good. Again, if you don't see the 24, you're just looking for the LCM, least common multiple of 8 and 6. You could make the list, counting up by 8s, or you could factor like we did at the beginning of your class. But some of you just looked at that and saw that the least common denominator is going to be 24. So let's go with that. What'd you do to the 8 to turn it into a 24? Multiply by 3. So what do we do to this 3? Multiply it by 3 to get 9. Now remember, 9 24ths and 3/8 have exactly the same value. They just look different. All we've done is change the appearance. Cut the slices of pizza into smaller slices. Now here, what'd you do to the 6 to turn it into a 24? Times 4. So what do we do to the 1? Times 4. 1 times 4 is 4. Again, 4 24ths and 1/6 have exactly the same value. We just changed the appearance. Now we have the same name, so what are we going to do? Add 9 and 4. Combine the counts. 9 and 4 makes 13. You had the right idea. And then what do we do with the denominators? We keep the same name. So we keep the 24. So 13 24ths is our answer. Now I'm writing this over again because we're going to play the what if game for a second. What if you looked at this and you didn't see that 24 was the common denominator, and you didn't remember how to do this least common multiple stuff, and you just wanted to get to doing the fraction and get it over with? Well, your calculators do the fractions. I showed you how to enter the fractions with the ABC key. You could enter 3 ABC8 plus 1 ABC6. It will spit out 13 24ths. So for your calculator, it's 3 ABC8. The ABC button on your calculator should be up towards the top. Or sorry, yeah, yours is down on the bottom, like the second one from the bottom on the left side. Yep, ABC8, then plus 1 ABC6. You hit equals and it should spit out 13 24ths. But if you didn't have the calculator or weren't using the calculator, if I have 3/8 and 1/6, a way to get a common denominator, again, not the smallest one, but it is a common denominator, is to just say, hey, what's 6 times 8? It is 48. Will that work? Sure. It's a little more difficult, but it works. 8 times 6 makes 48, so 3 times 6 is 18. 6 times 8 is 48, so 1 times 8 is 8. So I do have the same name, I have common denominators. I go to add, 18 plus 8 is 26 48. Now there's two things wrong with that. One, it's a little bit different answer than this. And two, if I look at it, I see that I can do what to it? I can divide both of those by 2, which gives me 13 24ths. which is the same answer I had here. So it's just by using that larger denominator, all you're doing is adding in the step of having to reduce it when you're done. And you're also adding in the confusion of working with larger numbers, which means you might be a little bit more likely to make a mistake. Let's have you guys try one. Three eighths plus 5/12. Give that one a shot in your notes. So of course, step one, I'm going to write this out vertically just because that's the way I do things. Step one is to find a common denominator. We could do 8 times 12 is 96, but we have a much more convenient one, which is 24 again. So now, what did we do to the 8 to turn it into a 24? Times 3. So what's going to go here? 9. I had to multiply the 3 by 3 as well. What did we do to the 12 to turn it into a 24? Times 2. So what's going to go here? 10. We had to multiply the 5 by a 2 as well. Now what? 9 times 10 is 9, or 9 plus 10 is 19 over 24. We keep the same name. How many of you had 19 over 24? Good deal. That one's a little simpler. If we're subtracting, what's that? Well, no, I meant it's a little simpler because everybody had it right, not that it's an easy problem and you shouldn't be proud of getting it right. So now what if we have something like 5/6 minus 2/3? First of all, we're subtracting now and not adding. But we still need to find a common denominator. We could do 6 times 3 is 18, but there's a smaller one we can use, which would be what? Just the 6. Sometimes one of the fractions already has the common denominator. So what goes here? 5. Yeah, there's no need to change that one. That fraction does not change at all. It stays 5/6. What's going to go down here? 4. We had to do 3 times 2 to make 6. So 2 times 2 makes 4. Now we are subtracting instead of adding. So it's not 5 plus 4. It is 5 minus 4 is 1 over 6. We keep the same name still. That's not so bad, is it? So anyway, let's have you guys try one. So let's have you guys do 5/6 minus 3/20. So, what is our common denominator going to be? 60 would work. Is there a smaller one? 30 is the smallest one. 60 would work. We just have to reduce it. Oh, wait. Never mind. Was 30 going to work? No. Okay. 60 is the smallest one. You're right. I owe you one. It's a Monday. Yeah. The 60s, yeah. We're 2 hours and 15 minutes into a math lecture. I'm starting to lose it. I'm sorry. So what's going to go up here? Careful.
50.
This will be 50. 6 times 10, so 5 times 10. What's going to go up here?
9.
9. 20 times 3, so 3 times 3. And now we are going to subtract. 50 minus 9 is 41 over 60. Very good. How many of you had 41 over 60? Cool. Well then, let's look at multiplication. Multiplying 2/3 times 1/5. When we multiply, do we need the same name? No, we do not need the same name. When we multiply, we simply combine the counts, and then we also combine the names. So our counts are 2 and 1. We combine them with multiplication because we're multiplying. What's 2 times 1? 2. Then we also combine the names, the 3 and the 5. What's 3 times 5? 15. So 2/3 times 1/5 is 2/15. Now we might have something like 3/4 times, let's see here, 2/5. What are we going to get? Well, 3 times 2 is 6. 4 times 5 is 20. Now, of course, what can we do with this? We're going to reduce. We're going to divide both of those by 2. You get 3/10. Now, some of you might be looking at this wondering, well, why didn't you? We could have cross-canceled before we multiplied. Why did you do that? Some of you right now might be wondering, what's cross-canceling? Well, we look at this and we realize this is going to become multiplying the numerators, 3 times 2, over multiplying the denominators, 4 times 5. And you see that both the 4 and the 2 can be divided by 2. So before we multiply, we could actually divide out that 2 from the 2 and the 4. 2 divided by 2 is 1. 4 divided by 2 is 2. So now when we multiply, 3 times 1 is 3. 2 times 5 is 10. So what basically all we're doing when we cross cancel, some of you heard it called cross multiplying, but there's another shortcut that's also sometimes called cross multiplying. So I want to avoid that term. But that cross canceling is just reducing before you multiply. Now in a problem like this one, it's about the same amount of work either way. We can, however, run into problems like this one. 24 over 25 times 35 over 36. We could go ahead and multiply that out and get 840 over 900. And then reduce it. That'd be a lot of reducing. Working with big numbers. I'm going to write that over here. Or we could look at this and realize, what can we cross cancel? Now, first of all, just like when I reduce a fraction, I always look for 10s and 5s first. Do I see anything here? Yeah. Both the 25 and the 35 can be divided by 5. What's 25 divided by 5? 5. What's 35 divided by 5? 7. So I've already reduced it a big chunk. Now then, there's nothing else to reduce there. 5 and 7 are both prime. I look at the 24 and the 36. Now there are a lot of things that both of these are divisible by. They're both even, so they can be divided by 2. They can both be divided by 3. Which means there's probably larger numbers, 6, 4, 12. 12 is the biggest one. In an ideal world, we would see that first and divide by 12. 24 divided by 12 is 2. 36 divided by 12 is 3. If we don't see that first, it's not the end of the world. Just like reducing a fraction, we could say, oh, 24 divided by 2 is 12. 36 divided by 2 is 18. Now we look at that, 12 and 18 can both be divided by 2 or 3 or 6 or whatever, right? We can just keep going and eventually we'll get down to 2 and 3 here. Okay, so it's just like reducing fractions. We don't have to find the largest number first. It's just easier if we do. So once it's reduced, now we have the 2 times 7, which is 14. 5 times 3, which is 15. If we reduce this, it would reduce down to 14 out of 15. Both of those are divisible by 60 if you want to reduce. Now, most of our examples are not going to be quite that drastic. Let's have you guys try one. Try that one for me quick. See what you come up with. So, first thing, now we don't have to cross cancel. We've already said you can reduce later if you prefer. But is there anything in this that we could cross cancel? Yes, we have 2 and 8. Both of them can divide by 2, which would give us what up here? 1 and 4. Then what? We just multiply, combine the counts. 1 times 3 is 3, and combine the names. 5 times 4 is 20. 3 20s. You could have done 2 times 3 is 6, 5 times 8 is 40, and then 6 over 40 would reduce to 3 20s. That's fine. How many of you had 3 20s? Good deal. It makes me feel better. We're batting 1,000 on the last few problems. So. And you guys know it's all about me, right? You're here to entertain me for 8 weeks this summer? Yeah. Okay, good. Good answer. Yeah, next week, at the end of next week, we're at the halfway point already. Yes, to celebrate our halfway point, I'll give you the following Monday off. Yeah. Okay, so.
Yay. Thank you.
Let's look at division. 12 25ths divided by 4 fifths. Now let's put aside what you know about fractions for a minute, or what you've already been taught about fractions. Just ask. I've said all along that division and multiplication follow the same rules. When I multiplied numbers, I just multiplied straight across. I combined the numerators and then combined the denominators. So when I divide, can I just divide straight across? Can I do 12 divided by 4 is 3? 25 divided by 5 is 5. Does that work? Yeah, is that the right answer? Yeah. Will it work every time? Oh, yeah. Why don't I do it that way? Well, the reason we don't do it that way is we run into problems like this one. If I went to divide straight across here, 3 divided by 2 is not a nice, neat answer, is it? 3 divided by 2 is 1.5, or 3 halves, or however you want to look at it. 4 divided by 3 is equally as ugly. It's 1 1/3. Doesn't divide nicely. How have you been taught to do that division? There you go. Just like when we were talking about subtracting with our negatives, you would change subtraction into adding the opposite. Same type of thing here. The first number does not change. The 3/4 is 3/4. It's not going to change. But dividing by 2/3 gets changed into multiplying by what we call the reciprocal, which is flipping it over, exchanging the numerator and denominator. So it's 3 over 2 instead of 2 over 3. And then we multiply. We've changed it from division to multiplication. So 3 times 3 is 9. 4 times 2 is 8. Now, of course, 9 over 8 we simplified to 1 1/8. So, what is the deal with this? Believe it or not, this first example I showed you is how dividing fractions is done. This dividing or multiplying by reciprocal is a shortcut. And I do want to take a couple minutes to show you where it comes from. Years ago, I mean a long time ago, even before my time, if I wanted to do 3/4 divided by 2/3, we would do this. In my fraction here, 2/3, I'm going to multiply the numerator and denominator. So 2 times 3 is 6. I am going to use that 6 to rename this first fraction. So I'm going to do 3/4. I'm going to multiply by 6 on top and bottom, which gives me what? 3 times 6 is 18. 4 times 6 is 24. Now that is still 3/4. We've just changed its appearance. And we're going to divide by 2/3. And now, just like we did up here, we're going to divide straight across. What is 18 divided by 2? 9. What's 24 divided by 3? 8. Same answer we got over here. So now the million-dollar question is, how did we get from this to this just flipping it over and multiplying by the reciprocal? It's not as far off as you would think. What we did here was this. We had 3/4. We multiplied by 6/6, and then we divided by the 2/3, right? Somewhere along the line, somebody looked at this and realized, hey, this here, if I did that piece first, 6/6 divided by 2/3, what's 6 divided by 2? 3. And what's 6 divided by 3? 2. What I get here is just this fraction flipped over. And what's left is the multiplying. So that taking the reciprocal and multiplying is just a shortcut for this longer, the actual real process of dividing fractions. We just skipped over a few steps. Now in practice, we are just going to take a reciprocal and multiply. But I wanted you to see where it comes from. There is actually, just like when I did long division on the second day where we did the repeated subtraction thing, there is a longer process. There is a reason why we do it that way. It's not just because I say so, which is too often the reason we're given in math. It just is. Do it. Okay, so let's take a look at some examples. Let's take 5/8 divided by, let's do 3/4. So 5/8 divided by 3/4. Am I going to do anything to the 5/8? No. The first number always stays the same. Just like when we were dealing with negatives and subtracting, we never changed the first number. But now it's going to be multiplied by either reciprocal 3/4 is 4/3. Very good. Now I could multiply here, but if we pause for a second, we'll notice we can do what? There you go. It's multiplication now. So just like any other multiplication, we can cross cancel. 8 and 4 both divide by 2 to give us 4 and 2. And now we have 5 times 2 is, actually I could still divide that out, couldn't I? I could have divided by 4 to give me 1 and 2, couldn't I? So you can see, like I said, you don't have to divide by the largest number first. You can divide it in stages. So now I have 5 times 1, which is 5. 2 times 3, which is 6. Very good. So my next example, 3/4 divided by 2, let's do 4/5. So my question for you, can I cross cancel the 4s? No. Why not? Yeah, it's not multiplication right now. It's division. We can only cross cancel in multiplication. This is going to be multiplication, it just isn't yet. What do we do to the 3/4? We leave it. It is 3/4. Then it becomes times 5/4. This is where we could cross cancel. Unfortunately, in this particular problem, there's nothing that we can cross cancel. So we're going to go ahead and multiply. 3 times 5, 15. 4 times 4, 16. 15 16ths. So we have to be careful. We cannot cross cancel until we have turned it into multiplication. So let's have you guys try 5/8 divided by 5/12. Do that one in your notes quick. So of course the 5/8 does not change. What's the rest of it going to become? Times 12/5. Do I want to take that 12/5 and make it into 2 2/5? No, we're going to leave it. We don't want to turn into a mixed number because we're in the middle of a process here, right? Now, what's next? Perfect. We can do a ton of cross canceling here. We can the 8 and the 12 can both be divided by 2, but also 4, right? 8 divided by 4 would be 2. 12 divided by 4 would be 3. And of course, the 5 and 5 are pretty obviously both divisible by 5. They're the same number, right? So 5 divided by 5 is 1 in both cases. Now pause. Any questions on how I got the 1s and the 2 and the 3? Okay. So now next, we're going to multiply. 1 times 3 is 3. 2 times 1 is 2. Are we done? No, at this point, we can turn this into 1 1/2. Now, in my math lab, there will be times where it just wants you to leave it like this. So make sure you look at it and it'll say whether leave it as an improper fraction or express your answer as an improper fraction or express your answer as a mixed number. Be careful. At this point, we're not dealing with mixed numbers a whole lot. So most of your homework that you will start today, it'll want you to leave it as an improper fraction. It's 3/2, just so you know. Now that we're feeling all good about this, a little bit of foreshadowing. So let's do this. What if we throw variables in here? Well, yeah, you're not totally wrong. Just like when we were dealing with our reducing fractions with the variables in them, we could separate the numbers from the variables. That's one possibility. Another possibility, if the numbers aren't too large, is we can just go ahead and multiply it and reduce it later. So I'm going to do this both ways. 5x times 3y squared. We multiply the counts. 5 times 3 is 15. Then we multiply the names. X times y squared is just xy squared. Nothing to really combine there. We're just putting them together. On the bottom, 4y squared times 7x to the 5th. We combine the counts. 4 times 7 is 28, y squared times x to the 5th. Now we're going to put them in alphabetical order because that's proper form. It's just x to the 5th y squared. At this point now, we reduce it. Is there anything I can reduce with the 15 over 28? Well, I'm writing it down already, so probably not. 15 and 28 have no common factors. Nothing we can reduce those by. But the x can be reduced how? Where's the largest power? Bottom. So that means the x is going to go on bottom. Now remember, this is x to the 1, so we're going to take the difference in powers. The difference between 1 and 5 is 4. 5 minus 1 is 4. The y, where's the largest power? They're the same. Guess what happens? They cancel out. That's 15 over 28x to the 4th. At this point, you don't have to panic too much about this. We will see it a little bit more later, but we'll talk more about it. By Thursday, we'll have talked more about it, unfortunately. Sorry. Or if we were adding fractions for common denominators. Let's say I had 3 over 4b plus 1 over 6. Looking at this, I'm trying to find a common denominator. Remember, common denominators are least common multiples. So I have 3 over 4b, 1 over 6, and I'm adding. My first step is to find that common denominator. So I am finding the least common multiple here. So 2 is just, or 4 is 2 times 2. 6 is 2 times 3. Now I'm not going to go ahead and, I'll do this in just a second, but before I finish this, what is the least common denominator for 4 and 6? 12. Okay, we know it's going to be 12. They have a 2 in common. This one has an extra 2. This one has an extra 3. That comes out to be 12. Okay? So we know 12 is going to go here. But what about the variable? Remember, for least common multiples, we take the, is it the lowest or the highest power? Highest for least common multiple. So we have the b there. There's no b here. So our highest power is 1. So it'll be b to the 1, or just b. So here, I have to turn the 4 into a 12, so I'm going to multiply by 3. Do I have to change the variable at all? No, it's already a b. So the only thing I have to multiply by is 3. 3 times 3 is 9. That becomes 9 over 12b. What do I have to do to the 6 to turn it into a 12? Times 2. Do I have to do anything for the variable? Yeah, there is no variable here, so I have to multiply by b to get a b in it. There is no b there, and I need one in my common denominator. So I have to multiply by not just 2, but 2b. On top, I multiply by 2b. What's 1 times 2b? 2b. Here's the part that kind of stretches your imagination a bit. Now that we have the common denominator, the 12b, we know that our answer is going to have a common denominator of 12b. For our numerator, we combine the numerators. What is 9 plus 2b? Stays 9 plus 2b. We can't combine them. Okay? Again, don't panic about those too much right now. We are going to deal with them more tomorrow. But for those of you that may have been considering not coming to class tomorrow, there's all the reason more that you might have to be here. So anyway, there is a new quiz. It is due tonight at 11:59 p.m. And there is a new homework. It is due tomorrow for class. Pretend that I wrote that so you can read it. Okay, good. You guys have a great day.